Okay, good afternoon, everybody. I think we're ready to go and let's get started. So welcome to today's AI for Net Zero webinar. I'm the chair today. I'm Simon Pearson. I'm Professor of Agri-Food Technology at Lincoln and Head of School of Agri-Food Technology and Manufacturing at Lincoln. And I'm also the Advisory Group Chair of the Bridge AI programme, which is a £100 million programme run by Innovate UK. Can I also introduce my colleague Sarah, so who's going to help with the chairing the session?
Yep. So welcome everyone to this session of the AI for Net Zero webinars. So I'm Pierre, TA Associate Research Associate at Georgios University, and happy to co-chair this session.
Brilliant, thanks, Sarah. And so really the objectives then of this the webinar, they're really a sort of a series to highlight the Net Zero for AI programme sponsored by UKRI, and it's to bring together experts, innovators, enthusiasts for artificial intelligence and sustainability, so trying to use AI to drive sustainability, and then ultimately to aim to help the UK and global society to hit net zero. So the aim is to really bring together a number of people from the AI community. Within the AI for Net Zero programme, we've got a very, very diverse range of different projects and applications. It covers many, many sectors of society, and it's all joined up by the horizontal, which is AI. And what the programme is trying to do is really focus on reducing emissions from the energy sector, transport sector, impacts on the environment, agricultural sector and food systems. So it's quite a diverse programme. And then we're really, really lucky today to have Georgios Rigas join us to give his presentation on real-time digital optimization and digital making for fluid-based energy and transport systems. So Georgios is going to give us a overview of his project, which is funded by the programme, over the next 35 minutes. And then there's an opportunity for lots and lots and lots of questions. So if you've got questions, please put them into the chat, into the comments section, and we'll Sarah and I will pick through them as well as we can. Before Georgios starts, just want to give a quick introduction to Georgios. So Georgios is a senior lecturer at Imperial in the Department of Aeronautics. Before joining Imperial 2019, he was a postdoc at Caltech and the University of Cambridge. Georgios received a PhD in aeronautical engineering from Imperial in 2015. His research is at the interface of digital modelling, optimization of complex fluid systems through use of applied AI. So he's particularly interested in development of real-time implementation of dynamic decision-making algorithms, which I think I'm really looking forward to that, Georgios. So decision-making algorithms to control turbulence in state-of-the-art wind tunnel experiments. Currently, Georgios is leading the AI for Net Zero effort at Imperial to increase the energy efficiency of energy and transport systems. So without further ado, I'm going to hand over to Georgios. You've got 35 minutes, and then we're going to come back to you with a load of questions if that's possible. So thank you, Georgios. Yep.
Thank you very much, Simon and Sarah, for the nice introduction. Actually, you introduced more or less what I will be presenting today, and the focus will be specifically, as you said, on real-time digital optimization decision-making for energy and transport systems. I want to mention that I'm going to give you just a small flavor of our work today, which is a collaborative effort between 4 institutions: Imperial, University of Edinburgh, Oxford, and University of Cambridge. So our focus specifically on that project is energy and transport systems, but we look at a specific common denominator that all these systems have that underpin the transition to net zero, which is the interaction with a fluid flow. So when we have wind turbines that will produce low carbon energy, they're interacting with the fluid flow of the air to extract optimally energy. We have aviation as well, that we have external aerodynamics, but also internal fluid flows in the combustion either of hydrogen or a sustainable aviation fuel. And I want to mention that aviation is a really hard field to decarbonize. And the third sector that is contributing substantially and actually is contributing a lot to the CO2 emissions at the moment is the road transport sector, accounting for approximately a fourth of the total CO2 emissions. So every time you have a system that is interacting with a complex fluid flow, it's really difficult to optimize its energy efficiency, and usually we end up with suboptimal efficiency. So the purpose of this project is to increase the efficiency of fluid-based energy systems and look in some applications in the three fields I just mentioned. And we're going to do that using AI, and specifically we're going to improve the efficiency to achieve our ambitious goals by 2050 for net zero, and hopefully to accelerate that to 2035. So not only we want to improve efficiency, but we want to see an impact in the acceleration of adoption of electric solutions, like in electric vehicles or hydrogen combustion, either in aviation as well in the road transport. And of course, through our work with renewable energies, we want as well to increase the efficiency of the production of low carbon energy. So how we're going to do that? We're developing the past few years, and specifically through this project, active learning algorithms, decision-making algorithms that they take actions on real time to improve specifically the efficiency of aerodynamic or fluid flows. And we're combining applied artificial intelligence to achieve that, meaning we implement in hardware in real time, in physical systems, the developed AI technology. Usually we need models that they perceive what the environment, this fluid flow, the state of this fluid flow is, and is taking an appropriate action to optimize the energy efficiency through interacting with turbulence. And turbulence is one of the classical physics problems that is still unsolved. The dynamics are chaotic, meaning that it's really, really difficult to predict them and thus to control them. And as I mentioned, specifically today, I'm going to be looking into two fields, specifically the road transport and the wind farm renewable energy sector. To achieve our goal, we have put together a team of people working in fundamentals of AI, specifically digital twins and decision-making algorithms, but as well practitioners and people expert really in the hardware implementation, of the efficient hardware implementation and of AI algorithms and the evaluation and training of them on high-performance systems. We're applying through field specialists our developed framework and technology to three different fields, as I mentioned: hydrogen, wind energy, and transport. And also we're trying as well to find the policy impacts of these approaches through knowledge exchange activities and evidence-based communication through the work at Cambridge. We also have industrial partners, specifically NVIDIA, for the implementation and the training of the decision-making algorithms, but also companies either in the aerodynamics or in the sustainable energy sector and consulting. And of course, all the work that I will be presenting today has been done by really talented PDRAs, which are part of these projects, and they really deserve all the credit for this amazing work. So we have seen a disruption the past few years using data and data-driven techniques to model various processes. And actually, in the physical systems, we have seen as well recently that large language models are able actually to predict the weather with up to 10 days using an unprecedented accuracy. And actually, at the moment, they are the most accurate weather prediction, or one of the most accurate weather prediction models, the ones developed using LLMs. And we have seen AI as well creating a big disruption in fields like autonomous vehicles. Reinforcement learning has enabled the autonomy in the fleets of road vehicles and other fleets of also aerial vehicles as well. But also we have seen a wide implementation of these techniques in robotics. Robotics, they learn to perform actions and take decisions in real time to achieve a specific objective. However, we haven't seen in any other physical systems a wide adoption of these decision-making algorithms, which specifically in the control community, they are well known all these years. So we'll be interchangeably changing the word control with decision-making. What makes it difficult? That the applications I was telling you earlier, they're governed by chaotic physics. But to our advantage, we have physical laws that describe to a certain extent, to a tractable extent, the evolution of the dynamics. So our goal to be able to enable the adoption of these modern AI technologies to the physical world is to combine our physical knowledge with the already existing advanced knowledge in the AI field. So specifically, we want to move from predicting the dynamics directly to decision-making. So learning what is the optimal actions we have to take to improve the efficiency in real time of fluid-based systems and make them adaptive, both to environmental disturbances, but also to the inherent dynamic nature of these systems. Probably the first disruption in the field with these decision-making algorithms was made by DeepMind when they demonstrated, by combining artificial neural networks and existing reinforcement learning algorithms, the ability to win Atari games like the one you see here. So the perception is the pixels we have for the game, the bricks and the ball, and the action is moving the lower part left or right. And you can see as we start learning how to win this game, we become better and better. After 100 episodes, we can consistently, with a few losses as well, hit the ball. But actually, as you're going to see, as the video goes along, the more we train, the better we become. And actually, after a certain number of episodes, exactly at this point, the decision-making algorithm is learning a really novel, non-trivial strategy that is able to win this game through a efficient tunneling technique. And as you can see, the ball has been trapped at the very top and actually is able to win in this game very, very fast. So now we're going to take some of these concepts, these efficient learning algorithms for Atari games, and apply it to real physical systems. And we're going to combine this with the physics that we already know. The reinforcement learning as a means of controlling systems has been also recognized from the energy catapult as a very promising approach. And we have seen already some industrial implementations of that. Not only for recommendation systems, as it happens with the most AI algorithms, but actually controlling physical processes like data center cooling or industrial process control. And it has been recommended by the Digital Catapult that the next few years we're going to see as well implementation to heat control processes, electric vehicle charging scheduling, but also the optimal interconnection of power networks and smart grids. And based on the introduction I gave you, hopefully the next step would be as well the implementation of these smart decision-making algorithms to more complex, chaotic energy systems. There is also disruption in the startup field, and there are quite a few startups actually that are leveraging these tools either in heat systems or in process control. One of these demonstrations was performed a few years ago in Google. Actually, they took the Atari game algorithm and they implemented it directly to the data center to find what is the optimal way to run the data center such that the energy consumption is minimized. So which parts and pieces they should be turned on, off, how the cooling should work, and so on and so forth. So recommendations are happening every 5 minutes. through this automated learning process. And as the learning becomes better and better, actually it was able to demonstrate by just turning on this algorithm, you can take a 30% energy efficient improvement with just a software modification in the operation of this power plant. So that happened quite a few years ago, and now we're trying to understand how these decision-making algorithms, as I said, can be applied to more complex systems. And we have seen a trend already coming also from the US. 10 years ago, they decided that the road transport sector can become much more efficient. So they added, for those of you that have been in California, these aerodynamic devices that are static. They're like a boat tail in the rear of the trucks. Tesla has been optimizing for many years the aerodynamics of the cars, and also probably the same will be happening with electric vehicles, because aerodynamic optimization is irrelevant with respect to the energy source, if it is fuel, if it is hydrogen, or if it is batteries, meaning that if you optimize the efficiency, you have longer range or larger efficiency and energy consumption. So the UK government as well, the last few years, changed the legislation to enable these aerodynamic devices to be part of the road vehicles. We have seen these devices being implemented as well in Europe, not only in the US. And actually, these flaps, they have been adapted as well to close so that they don't create any problems loading or unloading the trucks. And they give you up to 4 to 5% energy efficiency improvement, which translates directly to fuel consumption or energy consumption reduction. So what we have proposed at Imperial the past few years is that the flaps, actually, if you make them adaptive, so smart, they can improve much higher, 2 or 3 times or even 4 times higher efficiency than the static flaps. And why this is the case? Because every time the car is turning or there is a crosswind, the optimal static angle is not, of course, the one giving you the best energy efficiency. So we can learn a strategy that is changing the angle of the flaps, making them quasi-static, active, such that we increase the drag resistance saving. And actually, we have demonstrated that for various crosswind angles, we can achieve up to 12% energy drag reduction. And if we make the flaps longer, we can almost double this energy savings. So the question we're asking now is not only can we make the flaps quasi-static, but actually can we use smarter decision-making techniques such that we interact directly with the unsteady fluid mechanics, but also with unsteady dynamic environment, for example, turbulence that is coming from the free stream. And this is the question that I will be answering the next 5 minutes. Probably we're going to start increasing the complexity of the problem gradually, starting from very simple digital twins, which are simulations of relative low fidelity with respect to the realistic application. And we're going to move actually to wind tunnel scaled experiments of real track geometries to demonstrate that. So the framework we're using is reinforcement learning, as I mentioned, and we can have a digital twin for the environment. We have some wake sensors. These are the red dots in the wake of the car, and we can learn actually optimal decision-making algorithms. Here we are using a specific toolbox based on truncated quantile critics, TQC, or soft actor critic learning algorithms. And we play that game by either exploiting data that we already have or data that we learn, that we obtain in real time. So the goal is to reduce the drag by moving these flaps appropriately. And actually, we're able to demonstrate that we can learn very sophisticated control techniques as the one that I will show you now. So the flaps are doing just 2 minor motions. And here we have some hard nonlinear constraints, which make this problem even more difficult. And by doing this alternative up and down motion of the flaps, we're able to completely stabilize the unsteadiness in the wake of this representative road vehicle, very simple road vehicle here, and we can kill all the vortex shedding activity that is contributing to the drag. And of course, these algorithms now, they're dynamic, they're online, and in certain cases, they're generalizable as well, as we have shown. However, for practical applications, we cannot restrict the sensors. Only we cannot have the sensors in the wake. How would you measure wake when the vehicle is on the highway? So usually we rely on pressure sensors on the vehicle itself. And this is a common issue that we have in most implementations of these dynamic decision-making algorithms, that we have to sacrifice full observability for partial observability of the dynamics in order to reduce the net power save that I mentioned earlier. So what we found is that actually when we have full observability, we can prove both theoretically but also practically that we can get global minima using appropriate optimization algorithms. However, when we have partial observability, we can get only a percentage of the energy efficiency improvement. In that case, we can get only 30% of the energy efficiency compared to the 100% case when we have full information available. So the theoretical reason behind that is that actually all the processes involved in reinforcement learning to show convergence to this global minima or maxima have to be a Markov decision process, meaning that I have to know everything about the state of my system. However, this is not the case in most of the realistic engineering applications, but actually we can bypass that limitation by keeping a finite history of past observations and actions. And there are certain intricacies about that actually we have been working recently on, and we're able to solve them. One of the challenges is that we have to deal really with chaotic systems, so systems that are inherently unpredictable. And in that case, actually, we can get really good performance using recurrent architectures, or for chaotic systems, transformer-based architectures, like the work demonstrated by Max in this recent ICLR paper, where he showed how you can control optimally chaotic PDs with partial observations using transformer-based architectures. So combining all this together, meaning that we utilize all the past information we have in the current state of the observations, using both past measurements and past actions, we can discover optimal control approaches to optimize the energy efficiency. One detail that emerged and gave us some hard time throughout this procedure is that actually these problems become really non-convex. It's really difficult to computationally and algorithmically converge to the global minima or maxima. So we had to use specific categories of RL algorithms based on entropy maximization to explore the best way we can and exploit existing information also in the best way. So what we're able to show is that actually we can replace the information of the wake measurement, so all the information that supposedly we should have, but in practical application you don't have, by including past actions and options in the observation field. So this enabled us actually to obtain performance equivalent as if we knew everything regarding the state of this complex system, and we managed to decrease the drag and increase subsequently the efficiency of this body moving through the fluid. However, now we're going to try to scale up in more complex geometries. That was, from a fluid perspective, not a very complex case. The velocity of the vehicle was very low, so the flow was more or less predictable. And we're going to try now to go to full realistic turbulent regimes where you have also three-dimensionality of the flow, but also chaotic or turbulent dynamics. So the simulations in this regime become intractable, meaning there is no supercomputer at the moment that can solve this set of equations so that describe the fluid motion, which is Navier-Stokes. So either we have to rely on modeling, which still is very, very expensive to simulate these cases, or we can actually replace the simulated environment directly with a physical system. So in that case, we're going to replace the digital twin directly with the wind tunnel experiment, and we're going to implement in real-time reinforcement learning algorithms that they learn to optimize the fluid flow itself. So here, I'm going to show you some video from the training in one of the wind tunnels here at Imperial College. We have a benchmark road vehicle geometry, is known as the Ahmed body, and we have a set of flaps that learn how to optimally control the turbulent wake dynamics in the rear. And actually, we can see it is really fast. It's happening here at 30 hertz, 30 times per second. And the flaps are learning how to optimally increase the drag in this case. And of course, the sensors are only located on the base of the body. The past few months, we have been moving towards more realistic geometry. So this is a real track geometry scaled down 10 times. And also we're doing a realistic experimental procedure here. I mean, we have a rolling road to simulate experimentally here as reliably as possible the road vehicle dynamics. We measure the force to get the drag, and we have pressure on the base, and again, the same system of flaps. Actually, what we have shown by doing spectral analysis of the unsteadiness using the pressure, we're able to show that actually we decrease the unsteadiness in the wake quite substantially. These are preliminary results, and we envisage that the next few months we're going to increase even further the unsteadiness in the wake. I have to reemphasize that by reducing the unsteadiness, actually you reduce the losses, and the losses are counteracted by the fuel you spend to propel the road vehicle. So what we learned, to summarize from a technical point of view, that partial observability is a big fundamental challenge that has to be tackled to implement these learning algorithms in realistic engineering systems. And one easy way to bypass that is by encoding in a smart way past measurements. Specifically here, we're using either recurrent neural networks or transformers, depending on the complexity of the system itself. When you have to make a decision, you have to actuate your system. So the same problems appear as well with delayed actions. And in that case, you have to encode past actions in these models. Finally, we learned that these problems are very non-convex. In order to be able to find local minima, either we have to specifically constrain the problems within a certain set of solutions, or use entropy-based exploration, which we demonstrated can effectively actually converge to global minima instead of local minima if we don't use that. And we have learned quite a few things from the road vehicles, and now we're trying to actually apply all this reinforcement learning framework as well to the wind farm for optimizing the energy extraction. So one of the issues in the energy performance decrease that we have in wind farms is that once you put two wind farms, one behind the other, the second wind turbine sees the wake of the first one and reduces its energy extraction. So how low this can be up to 50% lower. And there are different ways actually that people have been studying to minimize this interaction. So you can rotate the bits of the blades, or you can yaw with active wake steering each of these wind turbines. So at Imperial College, Sylvain Lezé and along with his PDRAs, they have developed high fidelity models actually that they simulate with high fidelity the wake of wind turbines, and specifically the interaction of the wakes of wind turbines, as you can see here. So on the left hand side, we see two wind turbines. Actually, you cannot see the second one because it's hidden in the wake of the first one. But on the right-hand side, you can see two wind turbines where the first, with respect to the second, is actively steered at a different angle so that the wake is diverged so that it doesn't hit the second wind turbine. And with this wake steering procedure, actually, we can increase the efficiency of the interacting wake turbines. This has been demonstrated as well to different layouts of wind turbines. So here, this is a 4x4 wind farm layout. And actually, instead of optimizing its wake individually, like the greedy approach here, if we optimize the overall energy extraction of the entire wind farm, actually we can see a significant increase in the total power extraction from the wind farm. From approximately 17 megawatts for this specific case, you can go up to 21, and in the same time reduce also the fatigue by decreasing the fluctuations in the power. From an impact point of view, again, only with software modifications in the already existing wind farm facilities, even a very small performance improvement can actually yield significant increases in terms of power extraction. For example, this is the London array. At the moment, there are 175 wind turbines, approximately each of them 3.6 megawatts, which actually translates in powering 500 households in theory. So an increase of the power efficiency of 16% actually could power 80,000 more homes at no cost, and as I said, only with software modifications. So what is the next step, specifically only for these two applications? We want, first of all, to demonstrate the reinforcement learning algorithms for the wind farm, and ideally we would like to set up a pilot test to see how these perform in real environments. And the same applies for the road vehicle aerodynamics, to do some tests for scale 1-to-1 geometries. In the same time, we're doing work on the hydrogen combustion, and of course, our goal is to demonstrate in increased complexity environments the performance of these optimization algorithms. From a policy making and report point of view, we're putting together actually a framework for reporting guidelines for scientific machine learning, which we think is missing at the moment. And we believe it would be good to have some consensus on how we should be reporting either findings or setups for scientific machine learning. And feel free to get in touch if you have any ideas or if you would like to get involved. We're also actively participating in the decarbonization group that DESNAS and Catapults are coordinating along with the Alan Turing input to evidence the findings of our work. And stay tuned, we're going to be organizing the next, probably before the end of the year, a specialized training workshop on machine learning and RL for physical systems like the ones I showed you today. So with that, I would like to thank you for attending my presentation, and I'm more than happy to take any questions you may have.
Absolutely brilliant. It's Sarah. Oh yeah. So absolutely brilliant, George. Thank you so much. That was amazing work. Well done. Brilliant to see what you've done. It's incredible. Can I ask anybody who's got any questions to please put them in the chat, and then we'll come to them as quickly as you can. I'll just start with a really simple one. I mean, what you didn't really give us the acid test of what in the transport use case, what the fuel saving was optimized to be. And I'm just interested, what was the fuel saving, and what was the how much of that can you attribute to the AI that you've used rather than just conventional CFD type analyses?
Yes, that's a really good question, and actually, the scaling of that is something that we're still working on. But what I can tell you is that in this case, let me show you probably. So in that case, actually, 70% of the fuel you spend for a road vehicle is because of the aerodynamics. So if you optimize the aerodynamics, especially the unsteadiness, this can be translated directly to fuel savings. And in that case, 50% of this drag savings is because of that unsteadiness in the wake. In that case, we can completely remove that 50% of the 70%, which accounts for the unsteady aerodynamics. Now, when we translate that in the real wind tunnel, we can reduce the unsteadiness, but actually the percentages we have seen till now is up to 2 or 3% of aerodynamic drag saving. But we strongly believe that optimizing more this algorithm, making them more suitable for these systems we're looking into, actually can give more drag reduction.
Okay, that's pretty significant, nevertheless, isn't it? You're talking about huge industry with massive impact. So even a small savings big. And what's AI of that is? So that is the contribution from the AI. You couldn't have done that without AI on its. You couldn't have done that on its own.
Yes, exactly. Specifically, this case that I'm showing here. This case that I'm showing here, this is a hard constraint non-linear problem, meaning that we constrain the flaps and we're trying to find a really dynamic non-linear controller interacting with a high-dimensional fluid flow. So to my knowledge, there are no such controllers. Specifically, we've been looking for many years on linear controllers using linearizations of the underlying physical model, which actually were an obstacle to finding robust controllers. And now by bypassing completely the modeling part of the flow physics and asking the question in a reverse order, what is the optimal nonlinear controller such that the fuel efficiency is improved? Actually, it was reinforcement learning that gave us the solution.
Yeah. Okay. I'm going to go to Sarah, and then I'm going to come back. Then there's a question from Ming Wei. So.
Yep. So thank you very much for your talk. Very interesting and insightful. I would have a question regarding like the future prospect and challenges you see about control energy system and decision making with AI. Like for the younger generation, what do you see are the next challenges in your field?
No, so from my point of view, we have seen, as I mentioned also in the beginning of my talk, we have seen an incredible use of AI for recommendation for language-based models, and now is actually time to see the implementation in real physical systems and how this can be translated in actual findings and improvements. We have seen already some successful examples, like the optimization of real data centers which are really complex systems, and this is where these AI algorithms actually thrive. When you have really complex dynamics that it's really difficult to model, you can invert this kind of question and asking, what is the optimal way I can control these dynamics? There is a lot of work that is happening at the moment on decision making. Of course, reinforcement learning is not the only way, but it's a very promising direction. And have to be very careful. In many of the cases I showed you today, we're using also other types of optimization, like Bayesian optimization, if you want to discover quasi-static strategies. But if you want to find really dynamic nonlinear strategies, reinforcement learning at the moment is a really good way to tackle these systems. And we have seen the adoption in many fields, both for decarbonization, actually in industry, but also specifically for processes and process control. So definitely, this is something that we should keep an eye on, and specifically people that are working in these respective fields.
Right. Thank you.
And your algorithms, you've mapped it to a physics model, right? So have you been able to explain any new physics from what you've done, or is it still very black box, Georgios? Do we understand how it's improved the dynamics of an existing physics model?
Yes. I didn't mention one thing, not on purpose, but actually this is really expensive in terms of data requirements. Okay, it's not something that you do one simulation and you get your answer. They're data hungry. You need 1,000 simulations to get the result in this case. So people have recognized that, and there are not many ways you can bypass this model-free approach. The only way you can actually bypass that data hungry nature is to have a model. So now we're going a circle. So while you're discovering a control strategy, you're discovering also a model capturing the important physics that are responsible for the input-output relationship in this actuated system. So this now brings the category of model-based reinforcement learning, that you use a surrogate model simultaneously with the interactions with the environment to dream or unroll your learned model in the future and optimize what you imagine to be the performance of that system. So we think also this is a very promising direction. To answer specifically your question, and to be honest, this is something that we're working on, and we're really looking forward to interpret the dynamics of these discovered models that we get.
Okay, and what's your gut feel? Is it you're just improving parameterization, or are you finding some new second, third order effects or something that haven't been? So what's your gut feel? What's going on?
So it is really difficult to answer the question, what is the model that you should optimally control? However, if you find your optimal controller, then you can go back and say, what was that model that gave me optimal control? And by probing that, actually is again a question that we wouldn't be able to answer now, especially for a problem like turbulence. We have no idea for that kind of system what is a good model that we should use to control turbulent dynamics, because by definition, the discretized model is intractable in that case.
Yeah. It's fantastic. It's going to keep UKRI busy for a long time, isn't it? I'm going to go to Mingwai's question, if that's all right. So they say, thanks, Georgios, for the great talk. For learning to control the flap of the car, what do you think about Sim2 real techniques?
Absolutely. So transfer learning is something that actually definitely we should be using if we want to accelerate the training. So people do it in robotics all the time, because if you have a robot, you don't want to break it, you don't want to take an action and you fall down, and every time you fail, you break the robot. In our case, we don't fail here, but we are suboptimal in terms of energy efficiency. So it's not necessary for me to do sim to real. It's great if I want to accelerate the training, but it's not actually a constraint that we really have to solve at the moment. But definitely, if we can show how these techniques are transferable to and generalizable to different regimes, that would be great, which brings again the modeling perspective into this discussion. The only way you can have generalizable techniques is either you build your foundational models in such a way that they respect the physics, or directly you constrain the physics in this, so that you learn really generalizable strategies.
Yeah. Okay. Sarah, do you want to go?
No, I'm good. Nothing.
Yeah. Question next, Sarah, how do you get the data diversity to make sure these things are robust, Georgios? I mean, you've got wind tunnel things, which, very precise laminar flow, I assume, over the truck and stuff like that. And then you're going to go into the real world and you're going to have some really horrible, messy. So how can you, I just worry that you've got very, very non-diverse data going into the system. And I suppose that means you've got to get out to the real world a bit, doesn't it, to test it?
Absolutely. You're absolutely right. And we have progressively started increasing the complexity. So the flow that I show you here is a two-dimensional laminar case that is a simulation. The case we have, so the Reynolds number of that is 50. that quantifies the level of laminar or turbulent behavior. This is very laminar, but unsteady. Yeah. So in the wind tunnel is 200,000 approximately. A real car is a few millions. So we're very close to realistic turbulent regimes in these national wind tunnel facilities we have here. Answering technically now your question, we can ensure, because we know we're turbulent and turbulence is ergodic, that we explore the entire phase space because of this property of turbulence, of ergodicity. So we're sure that we explore the states because we see everything. Regarding the actions, it was the entropy reinforcement learning algorithms that we really have to add a lot of entropy in the exploration of the actions to make sure that we have all these constraints with the neural networks and we really converge to the best global minimum. So definitely. And actually, surprisingly for us in the beginning, this entropy exploration makes the algorithms very, very robust. These are usually stochastically framed, these algorithms. You have a Markov decision process, and for the underlying process and for the feedback, you have a stochastic policy as well, which seems to be very robust. But of course, all this is to be tested in a real environment. So
yeah, that's fantastic. Unless Sarah's got another question, my final question is really for you. Really, it's about your personal journey, which I find really interesting. So you started off as an aeronautic engineer, PhD how have you adapted to sort of new techniques like AI? How have you stepped into that world? Have you bridged that gap? Do you consider yourselves as an aeronautics engineer or an AI engineer? What's your journey, and where do you see that going?
Actually, when I did my PhD here at Imperial, I did it on experimental fluid mechanics, and I found a big wall that I couldn't understand what I was measuring as an experimentalist. And actually, this motivated me to look a bit more into the theory. And as soon as I looked into the theory, there was another world that came up, that theory of computations to approximate using discretized models or of the governing equations, or make predictions of the model. So I ended up at Caltech and at Cambridge working in computational science. And I've been really, really open about new techniques and exploring. It's like we do a maximum entropy reinforcement learning for our learning. And definitely what I want to say is people should be always open to ideas. We should be trying constantly different topics. There is not only one solution in everything, and only by testing and making appropriate hypotheses and testing, we can tackle these really difficult problems. In my case, I was lucky because my background was at the interface of experiments and computations, and this allowed me as well to bridge that gap. AI for me was just a tool to solve the problems I had. And when I saw the impact, the more you look into it, the more you start thinking, oh, I could apply that in so many different applications, which make it very, very enjoyable and keep us excited.
Well, thank you. Unless Sarah, have you got any more questions or?
No, but I mean, this is a really inspiring conclusion, I would say. So thank you for that.
Yeah, thanks, Georgios. It's great, and it's great to hear your own journey, because we need more people to actually walk that journey as well. And if people like you have done it and you can inspire others, well done, mate. So brilliant. So great job. So that's it. I'm going to let everybody have 12 minutes additional time, if that's okay, and close it out now. So I thank everybody for joining, and I thank Georgios and Sarah and Annie May in the background, who's keeping us in order. That was really fantastic, and it's great to hear. And I think same time next week or sometime, I think the next one. So thank you very much. So that's it. So thank you.
Thank you.